In this video, we're going to prove one of the most amazing facts in mathematics. That is that E, the number E, is transcendental. So I'm not going to explain what it means to be transcendental. Maybe I'll do that in another video, but basically it means it's not algebraic and it's not something like 2 or like 10 or root 2 or even I for that matter. Those are all algebraic numbers. E is something different. It's something that kind of transcends algebra. Think of it that way. So we'll start off the proof with a function f of x, and it's going to be a polynomial of degree r. The reason we're not using n is because we're going to use that for another purpose later, but it's just some polynomial of degree r. And and then we'll define a second function, g of x, which is going to be comprised of the derivatives of all the derivatives of f of x, so up to f prime of r. Because if you think about it, f to the r plus 1 is just going to, and all subsequent derivatives of f is going to be equal to 0. We can take the polynomial, say x squared. So the first derivative of that is 2x, second derivative is 2, and all subsequent ones are 0 because it's just going to be the derivative of a constant. So we have the definitions for a function, so now we're going to let's take the derivative of this guy. And so the reason we're going to do this is we'll get a nice relation at the end, and what we're going to exploit is the fact that the derivative of e to the x is e to the x. So this is not going to be the case if it was just some other constant. That derivative is natural log of a times a to the x. So we get this nice guy. So e to the negative x times g of x. And we're going to compute the derivative. We'll just use the product rule. Negative e to the negative x, g of x, plus e to the negative x, g prime of x. And so this term right here, we know g of x is equal to f of x, f prime of x, plus all the way up to f to the r of x. And so now g prime of x prime equals f prime of x plus f prime of x plus f to the r plus 1 of x. And so we know this is just equal to 0. And so we can say g prime of x equals g of x minus f of x. See, because it's just g of x without this term right here. So now we can say that the whole thing so if we put this up here, that will be g of x. This is negative e to the negative x g of x. This is positive e to the negative x times g of x. And so that will cancel out, and we'll just be left with negative e negative x times f of x. So now that we have that nice relation, it's time to assume that e is algebraic. I'm not going to go into why we define an algebraic number like this. Maybe I'll do that in another video, but just for brevity, we will define e to satisfy this relation. So c sub n times e to the n plus plus c2 e squared plus c sub 1 e to the 1 plus c sub o equals 0. So if e satisfied this relation, it would be algebraic, and we're going to assume this, and by assuming it, we'll eventually get a contradiction from that relation that we got earlier. And once we get the contradiction, we can say that our assumption that e is algebraic must be wrong. This is something that most calculus students will remember. That is the mean value theorem. So this is the usual calculus definition that some function, we'll call it h, the slope of the tangent line at some point c will be equal to the slope of the secant line on some interval. Usually in calculus you use a to b. We'll just use x1 and x2 because it's easier for our purposes. So for this proof, because it'll come in handy later on, we will use the definition that c equals x1 plus theta x2 minus x1. So now theta is what we're varying, and we have c in terms of the interval that the slope of the secant line would be on. So now, if we rewrite it, we have h prime of x1 plus theta x2 minus x1 equals h of x1 minus h of x2 all over x1 minus x2. So we will apply it to the function we had earlier. So that is make h of x equal to e to the negative x times g of x. And we'll make this on an interval x1 equals 0 to x2 equals some constant k. So now we just found out what h prime of x was. So we have, negative e to the negative. So this is c, which we defined as x1 plus theta times x2 minus x1. But this is just 0. This is k, and this is 0. So this just turns out to be e to the negative theta k, and same goes for f of x, so that's going to be theta k, equals e to the negative 0 times h of 0 minus e to the negative k g of k, all over 0 minus k. Now if we simplify that relation, we will get that g of k e to the negative k minus g of 0 equals negative e to the, negative k, because we multiplied through by k, e to the negative theta k, f of theta k. And so now we will multiply through by e to the k, which will make this term equal 1. And we arrive at the final relation, g of k minus g of o e to the k equals negative k e to the 1 minus theta k f of theta k. And so this theta is going to be specific to this k value, so we'll call it theta sub k. So now this we can then use by combining our assumption that E is algebraic to find a contradiction. So let's start plugging in specific values of k. So that is k equals 1, 2, ... to some value n, okay? So we get g of 1 minus g of o e to the 1 equals negative e to the 1 minus theta k. Sorry, this is theta 1 times 1 f of theta 1 g of 2 minus g of o e squared equals negative e to the 1 minus theta 2 times 2 f of 2 theta 2 all the way to g of n minus g of o e to the n equals negative e to the 1 minus theta n f of n theta n. And just for brevity, since this right term doesn't matter, we're going to call this epsilon 1, epsilon 2, and epsilon n. So now what we're going to do is, let's see what color, let's go with green. We're going to multiply through by C1 and all the subsequent C values that we had when we assumed that E was algebraic. I don't have room here. Cn. So 1 second, I'll clear. Now when we simplify that all down, we get that C sub 1 times G of 1 plus C sub 2 G of 2 plus all the way to C sub n G of n minus G of O times C sub 1 e to the 1 plus C 2 e squared plus C to the n e to the n, and that all equals C1 times epsilon 1 plus C2 epsilon 2 plus all the way C to the n epsilon n. So now this value, since we assumed that this was equal to 0, except we don't have the C sub O value, so this is negative C sub O. So the final relation that we get is C sub O G of O plus C1 G of 1 plus C2 G of 2 plus all the way C to the n G to the n equals C sub 1 epsilon 1 plus C sub 2 epsilon sub 2 plus all the way C sub n epsilon the n. And this is something we're going to box because it's very important. Up to this point, we have assumed any value of f of x and subsequently any value of g of x. Everything we've done applies to any function f of x and g of x. So now we're going to assume a specific function of f of x that was first used by Hermite. And he used this in a couple of proofs, so we're going to use it in ours. And it looks a little funky, but it's not that funky. And so P is going to be any prime number. It will be greater than n and greater than C sub O. And we'll use these later when we start talking about divisibility, but first we're going to look at what happens when we take the derivative of f of x, because then that will tell us something about g of x. So let's analyze this at some value j, and that can be any integer 1, 2, 3, up to n. So because of these parts right here, we know that f of j will be 0 immediately. That's quite obvious. But what's going to happen when we start taking the derivative of f of x? So we can think of it, f of x, as this, minus x p of x. And so k, or I'm going to call this j. I don't know why I called it k. So j is just going to be some value in here between 1 and n. It could be 1 and it could be n, but we're going to some arbitrary value. And p of x is going to be just the rest of the function. And so now if we apply the product rule, we will get that f prime of x is p times j minus x of p minus 1, or to the power of p minus 1, times p of x plus j minus x p times p of x, or p prime of x. And so now what we have is if we put in f prime of j, we will get 0 because of these parts of the function. And this argument will work for any derivative of f of x up to p minus 1, because that's when these terms will start running out at the p minus 1th derivative. So we've shown that for any value of j, that f of j equals f prime of j equals f double prime of j equals up to f to the p minus 1 of j, which equals 0. So now we need to figure out what happens after this, because f of x is a function to the rth degree. And so we want to know what happens at the pth derivative, at the p plus 1th derivative, all the way to the rth derivative. So another way to write this function, if you multiply out all the terms, is n factorial to the power of p minus 1. And I'm not going to go through why this is the case, because just for brevity. If you want to go through it, I assure you that this is what happens. This is just some integer, x to the p over p minus 1 factorial plus x to the p plus 1 p minus 1 factorial. And so this will be, and I'll write the generic. This is going to be b to the n, x to the p plus n over p minus 1 factorial. So I should have wrote ... in here. But this is what ultimately the function will go out to. And so now we can see, once you take the f to the, I'll do this another color, the pth derivative, no matter what, so this term will go to 0 because of that exponent. And what's going to be left is p factorial times something plus p plus 1 factorial times something x to the 1 plus, and this will be p plus 2 factorial over 2 and x squared, so on and so forth. But there will always be this multiple of p through every term. So all subsequent derivatives of f of x after the p minus 1th derivative will have some value of p in front of every term. So therefore, all those functions are, or all those derivatives will be divisible by p. What we can conclude from all this is something about g of j, because this is going to be equal to f of j plus f prime of j plus f double prime of j plus up to f to the p minus 1 of j plus f to the p of j plus f to the r of j. And so we know that these guys are all going to be 0, and we know that these guys are divisible by p. So we can say that p divides g of j for values j equals 1, 2 to n. So we have looked at g of j and f of j for values 1, 2, 3 up to n, but now let's look at g of 0 and subsequently f of 0. So we know that f of 0 equals 0 because of the x to the p minus 1 term. And we know that that's going to be equal to p prime of 0 and p double prime of 0 all the way up to p minus 2, because that's when that x to the p minus 1 term is going to run out, is at the p minus 2th derivative. So at f of p minus 1, that's going to be equal to n factorial times p. And if you look at the term definite, or the adding definition of the function that I gave, this makes a lot of very intuitive sense. So we can say that since p is greater than n, that's how we defined it, that p does not divide n factorial. Because since p is greater than n, it can't possibly divide. It's like saying 10 divides 2. It doesn't make any sense. So therefore, that means therefore, p does not divide f to the p minus 1 of 0. Since p doesn't divide f to the p minus 1 of 0, and g is made up of all the derivatives of f, we can conclude that p does not divide g of 0. So now that we know what g of 0 and g of 1, g of 2, g of 3, all the way to g of n are, let's look back at the original relation we had, mainly that c sub o plus g of o, or is times g of o plus c sub 1, g of 1 plus all the way c sub n, g of n equals c sub 1 epsilon of 1 plus c sub 2 epsilon sub 2 plus all the way c sub n epsilon of n. So up to this point, we've been using epsilon as a placeholder just for simplicity, but now let's actually examine what epsilon is. So if you remember, epsilon of I, we'll use I since we've already used k, equals negative I e to the I times 1 minus theta I f of theta I times I. And so now if we actually substitute what we've defined f of x to be, we get e to the I of 1 minus theta I times I theta p minus 1 1 minus I theta p minus, 2 minus I theta p all the way to the n minus I theta p. This is all times I, that's negative, and p minus 1 factorial. So now we're going to simplify this because that's kind of messy, so that the magnitude of this is going to be less than or equal to. So now we know I has to be less than n. And so since theta is between 0 and 1, we can say that this whole thing is going to be less than this. Okay? And so using the same argument, we know that this will be all less than, I'll use a different color really quick. We know 1's going to be greater than this, 2's going to be greater than that, and n's going to be greater than this. So we can say that this whole thing is going to be less than n factorial to the p. Right, because 1 times 2 times 3 all the way times n to the power of p, all divided by p minus 1 factorial. And I almost forgot this part, but n is obviously going to be bigger than this, so we can just say times n to the p. So now we will examine this definition of epsilon. So we know that the magnitude of some value of epsilon will always be less than or equal to e to the n times n to the p and factorial p all over p minus 1. And so if we take the limit as p goes to infinity of epsilon, this is approaching 0, right? Because as p gets really, really big, this value is going to just shoot to infinity, and this whole thing will shoot to 0. So therefore, what we can conclude is that as p gets very big, this whole thing, c sub 1 epsilon 1 plus c 2 epsilon of 2, oops, epsilon of 3 plus e sub n epsilon of n, is going to approach some value less than 1. But we know that each of these terms has to be an integer. We've defined all the c's to be integers. And if you look at all the epsilon terms, there's nothing in them that would produce a fraction. And these have to be an integer as well. So the only integer less than 1 is 0. So we can say as p gets very large, this whole expression will approach 0. and has to be equal to 0. And so from that, what we can conclude, what is this equal to? This is equal to C sub O G of O plus C1 G of 1 plus Cn G of n. So we can conclude that since this must be approaching 0 as p gets very large, this must also be approaching 0 as p gets very large. So using what we know from earlier, that p does not divide G of O, we can conclude that G must also not divide C sub O G of O plus C sub 1 G of 1 plus C sub n G of n. That bothered me. I'm going to redo the n. But we know that as p gets very large, this approaches 0, and p definitely divides 0. Or sorry, it does divide 0. So we've reached a contradiction. If this is approaching 0 and p doesn't divide it, that doesn't make any sense. So therefore, our initial assumption that E was algebraic was wrong, because that's what led to this contradiction. So therefore, we can conclude that E is transcendental. And we're done.